Did you want to retake the test? I'm sorry?
Is that the only purpose for taking that?
No. Did you want to retake the test?
Yes.
All right, we'll get started in about 1 more minute. Did you want to retake the test?
Yes, sir. Thank you.
All right, we'll go ahead and get started. All right, so remember I did send you the study guide for test number 4. And so the study guides, if you go to the table where it says study guides, you go here, and it says study guide test 4, Wednesday, April 27th. Now I know you had a test last week, but remember the test was supposed to have been the week before last week. But at one point I mentioned when I told you about test 3, I also told you test 4 would be on that last Wednesday after spring break. So it's the 27th. And then the week after that is the last week of school. All right, so you go here to access the study guide. And so there's the link to the study guide and then some information that you may want to look at as well regarding some topics that are on the study guide. Those of you that just walked in, you need to take the test?
Okay.
Okay. You need to take the test? You need to take the test? You good? Okay. Okay, so there's something on there about inverse of a rational function. On the final exam, they do have something about the inverse of a rational function. So make sure you look at that topic. So they're going to give you a rational function and you have to find the inverse. And then there's the end behavior of a polynomial function. There's something on the final with that as well. And then exponential functions and applications. So on the final exam, there is an application on compound and continuous interest. So it's very important when studying for test number 4, you also keep aware of the fact that those topics down here are also on the final exam. All right, and your final exam is that Wednesday, May 11th, I think. That's a Wednesday. So if you go to the BRCC's website, they tell you what the times are. So you're not going to like this time. So if you go to academics, final exam schedule. All right, so there's the final exam schedule for spring. You scroll all the way at the bottom, we are on Wednesday. So scroll to Wednesdays. So this is Thursday, here's Wednesday. So Wednesdays, it's a little confusing, but Wednesday's classes start here. So ours is right here. See where it says 5:45 p.m., 6 p.m., 6:30. So any class that starts at that time, which ours does, on Monday and Wednesday, is at 8:30 p.m. that night. So from 8:30 to 10:30, that's when your final exam is.
In person?
Mm-hmm. Yeah. So keep that in mind. All right. And don't ask me if we could do it on that 6:15 because there's probably another class in here at that time. So ours is at 8:30 p.m. on Wednesday, May 11th. Okay? Okay, so let's go then. All right, so I told you about the study guide. I told you where it's located. All right, remember these are, if you go to week 13, that's where the agenda is. Week 13, I listed the study guide several places. I listed it here, I listed it here, and I listed it under study guides that I just showed you. There's always someone that will say, I don't know where it is. Well, it's 3 places. All right, and don't forget, your agenda for week 13 is right here. And so today we're going to look at exponential functions, graphing. We're going to look at zeros of polynomials, the rational zeros theorem, and then we're going to start talking about properties of logarithms. All right, so let's start talking about with Monday's agenda. So Monday's agenda was on exponential functions, graphing exponential functions. Now you did some of that last week. You had to turn, I don't know if you had to turn it in, but it's, let me go back and check. It was, if you go back to last week's, so you go back to last week's agenda, week 12, so 5.1. Yeah, so 5.1, you started talking about graphing exponential functions. So at 4 and 5, you had to turn in, and then worksheet 6 was not to be turned in. So you started talking about graphing exponential functions. What we're going to do here, though, is talk about horizontal shifting, shifting left, right. Last week, you talked about shifting up and down. This time, you're going to look at shifting left and right. On the final, the one that you have to graph is going to be a horizontal shift. The final exam, you're going to have to graph an exponential function, and it's going to involve a horizontal shift, not a vertical, horizontal, okay? All right, so let's look at that topic. All right, so they updated the whiteboard so it looks different than the last time we did this. All right, so this is section 5.1. Exponential functions. Okay, so last week you learned how to graph this. This was last week. So number 1, graph f of x equals 3 to the x minus 4. So if you were to ask to do this using transformations, which on test 4 you could, this could be on test 4. If you were asked to do this using transformations, what would you do first? What would you graph first? the parent function. Parent function in this case would be 3 to the x. So the first thing you're going to do is you're going to graph. So step 1 is to graph y equals 3 to the x. All right, so now I can't bring in an image here. They won't allow me. They updated this. So there's nothing here that says I can upload a document. So I'm going to draw this by hand. So I can't, like I did last time where I could bring up some coordinate grids, I can't do that here. All right, so when doing the parent function, you can use a t-table for the parent function, y equals 3 to the x. So if x is 0, I get 3 to the 0. And what's 3 to the 0 power? 1. When x is 1, I get 3 to the first, which is 3. When x is 2, I get 3 squared, which is 9. When x is negative 1, I get 3 to the negative 1. And if you studied last week's lessons, and this comes back from a previous course, what is 3 to the negative 1 the same as? 1/3. If x is negative 2, I get 3 to the negative second power. And what is 3 to the negative second power the same as?
1 to the 3 second power.
Okay, so remember to rewrite negative exponents, this was in the previous course. To rewrite negative exponents, you're going to write it as 1/3 squared. So 3 to the negative second is equivalent to 1 divided by 3 squared. And 3 squared is 9, so this is 1/9. Now when you graph the parent function, what is the horizontal asymptote of the parent function? Don't just say 0, you're going to say y equals 0, which is the x-axis. So when you graph from the parent functions, you're going to put a dotted line on the x-axis, because that's the horizontal asymptote for y equals 3 to the x power. So when x is 0, my y value is 1. When x is 1, my y value is 3. When x is 2, my y value is 9. 6, 7, 8, 9. It's not scaled very well. When x is negative 1, my y value is 1/3. When x is negative 2, my y value is 1/9. When you studied those lessons last week, what did you remember, or what do you remember about those y values as x approaches negative infinity? So as your x values get smaller and smaller and smaller, what does those y values approach? Do you remember? They approach the horizontal asymptote. So they don't cross a horizontal asymptote, they approach it. And on this side, it rises very rapidly. All right, so this is the graph, y equals 3 to the x. So I graph, so step 1 is to graph the parent function, which I just did. What is step 2? Shifted down 4 units. So everything is shifted down 4 units. So step 2, shift y equals 3 to the x down 4 units. So everything is shifted down 4 units. So you can move everything down. So the horizontal asymptote, I'm going to shift down as well, 4 units. 1, 2, 3, 4. So I'm going to go ahead and use a different color. So here's my new horizontal asymptote. What's the equation of that horizontal asymptote? Y equals -4. Don't just say -4. It's a horizontal line, so you got to say y equals -4. And every point on the parent function is shifted down 4 units. So all you do is look at the points that you used here, and you just shift them down 4 units. So for example, this one here, I'm going to go down 4 units. Now it's not scaled very well. 1, 2, 3, 4. This point here, I'm going to go down 4 units. 1, 2, 3, 4. And then this point down 4 units, that's about here. And then up here, 1, 2, 3, 4. And then you just do this. Make sure you draw an arrow. And remember, in the lessons, you were told, don't make this part here look like it's crossing the horizontal asymptote, because it doesn't. It gets closer and closer and closer to it without touching or crossing. All right, don't make it look like it goes back up either. Some students do that. They do something like this, and that's not true. Okay, it goes towards that asymptote. Kind of looks flat at some point, but it's not. All right, so everything is shifted down 4 units. All right, so that's a vertical shift. On your final, they're going to ask you about a horizontal shift. So let's do this one. So this is number 2. Oh, before I go on, let's look at this example. All right, so this same problem, and then here's an item. So the point 481 is on the graph of y equals 3 to the x. Kind of makes sense, because if I did that on that t-table right here, when x is 3 and I do 3 to the 4th power, I get 81. All right, so the point 481 is on the graph of y equals 3 to the x. This point translates to what point on the graph y equals 3 to the x minus 4. What do y'all think? So if you're told that the point 481 is on the parent function, and you're asked, this point translate to what point on the function on a graph, what would you do? Subtract what by 4? Okay. So remember, this is a vertical translation, right? Minus 4. So you're going up and down, correct? In this case, you're going where? Down. Well, when you go up and down, what coordinate stays the same? When you look at this right here, what coordinate stays the same? The x. What changes? The y changes. So I'm shifting every point down 4 units, right? So for example, when I did this one here, this was 2, 9. It became what point? 2 what? When I shifted 2, 9 down 4, it became what point? 2, 5. So when you're doing a vertical translation, you're only dealing with the y coordinate. So the point, so your answer is going to be 4 comma, and then all you do is take 81. I'm not sure why this line keeps drawing right here. Take 81 and subtract what, 4 from it? And what's 81 subtract 4? 77? So there's your answer. So you have to remember that with vertical shifting, the x coordinate stays the same, the y coordinates change. So you can take the y coordinate and you're going to subtract, in this case, 4 from it, because you're shifting it down. All right, now let's look at a horizontal shift. All right, so example. All right, so let's graph f of x equals 3 to the x plus 5. All right, now be careful, I'm not saying this. Those are two different things. This is what kind of translation? Vertical translation. This is what kind of translation? horizontal. So when the numbers with the variable, that's a horizontal translation. And so with this horizontal translation, remember with horizontal translation, you always think the opposite of what you would do. So you would not shift it 5 units to the right. In fact, you would shift it 5 units which way? To the left. Okay? So step 1 would be to first of all graph the parent function. So let's graph the parent function. What's the parent function? Okay, graph the parent function. Which is y equals 3 to the x, which we've already done. But let's go ahead and do it again. All right, so when x is 0, my y value is 0. When x is 1, my y value is 3. When x is 2, my y value is 9. 3 squared is 9. 7, 8, 9. And then your horizontal asymptote is what line for the parent function? What's the horizontal asymptote? Y equals 0. So remember the horizontal asymptote is y equals 0, which is the x-axis, right? So you put a dotted line on the x-axis to represent the horizontal asymptote. And you know that on this side it rises like this, rises rapidly, hence the idea of the exponential function. And on this side it goes towards what concept on this side? You got to say it goes towards the horizontal asymptote. Does it cross a horizontal asymptote? No. Does it touch it? No, something like that. So there is y equals 3 to the x. That's step 1. So you graph the parent function. Step 2 is to take the parent function and shift it which way? 5 units to the left. All right, so on your final, that's what you're going to do. You're going to graph the parent function, and then you're going to say, step 2, shift y equals 3 to the x, 5 units to the left, in this case. So every point is shifted to the left. The horizontal asymptote stays the same, correct? It's still y equals 0, the horizontal asymptote. Every point is just shifted to the left 5 units. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then this one also. So that was at 2, and then 3, 4, 5. It's not scaled well. Kind of messed. I'm drawing this by hand. That's why it's a good idea to have graphing paper. This is horrible. Let me erase this. 2, 3, 4, 5. Let me put that right here. All right, if you had graph paper, it would look better. So everything is shifted to the left 5 units. Now the one you're finding, you're gonna have graph paper, so you don't have to worry about doing this by hand. Online people, you need to make sure you have graph paper on the final. Spend some money, find a relative that has a printer and print graph paper. Okay, now, any questions on this? All right, now, suppose I ask this question. The point 6, 729 is on the graph of y equals 3 to the x. In fact, you use your calculator. 3 to the 6th power is 729. This point translates to what point on the graph of y equals 3 to the x plus 5. What do you think? So one of the worksheets. On the worksheet, there's a whole set of problems that ask you those questions. First of all, you have to know the translation. Which way are you going? To the left. So when you move to the left, when you take a point and you move it to the left, what changes? What stays the same? What stays the same? The y coordinate stays the same. What changes? You can even see it right here. What changes? The x changes. So when you move to the left, if this is 5, when you move to the left, those numbers become smaller, doesn't it? So if I'm moving to the left, do I add or subtract from 6? I subtract. What do I subtract from 6? What do I subtract from 6? 5. You moved it to the left 5 units, right? So my new point then would be 6 subtract 5 becomes what? 1. And then what's my y value? 729? There's your answer. Did you need to retake that test?
Yeah, I needed to take the test, but I think I got it all mixed up. Was that the student online?
No. Do you want to take the test now?
Please, if you
Okay.
don't mind.
All right.
I'm so sorry.
It's okay. All right, now let's look at this example. The point -7, 128 is on the graph of y equals 1/2 to the x. And you can always verify that, because look, if x is -7, what's 1/2 to the -7th power? How do y'all do that? You got to remember some things you've learned in a previous course. How do I make that exponent positive? Take the reciprocal of the base. What is the reciprocal of 1/2? 2. So I get 2 to the 7th. So 1/2 to -7 is equivalent to 2 to the 7th. Now on your calculator, 2 raised to the 7th power is going to be 128. So that's where I'm getting this. So the point -7, 128 is on the graph of y equals 1/2 to the x. This point translates to what point on the graph of y equals 1/2 to the x power plus 20. How would you figure out that answer? Do you need to retake that test?
Yeah, sure.
Go and sit in the first 4 rows. How would you do this problem? Okay, so plus 20 means going up 20, right? So that's a vertical shift. So when you do a vertical shift, what coordinate stays the same, what coordinate changes?
X stays the same.
The x stays, so if you take a point, just visually look at this. If I take a point and I shift it up 20 units, right? The x stays the same. What changes? The y changes. And how does it change in this case? Plus 20, add 20 to the y coordinate. So the answer will be -7, and then for the y coordinate, you're going to say 128 plus 20, which is 148. All right. And then let's do one more example. The point -6, 729 is on the graph of y equals 1/3 to the x. And you can always verify that, because if you take 1/3 and you raise it to the -6 power, how do you make that exponent positive? Take the reciprocal of the base. It's called the base. Reciprocal of the base. What is reciprocal of 1/3? 3. 3 to the 6, when using your calculator, is 729. All right, so the point -6, 729 is on the graph of 1/3 to the x power. This point translates to what point on the graph of y equals 1/3 to the x minus 15 power. So you have to know what kind of translation this is. So y equals 1/3 to the x minus 15. What kind of translation is this? Horizontal which way? To the right, how many units? 15. So I'm going to take this point, I'm going to shift it to the right 15 units. So when I shift a point left or right, what coordinate stays the same? The y coordinate stays the same. What coordinate changes? The x. So what do I do to this x coordinate that's -6? I add 15 to it. So the answer, so my y coordinate is still 729. My x coordinate, I'm going to say -6 plus 15, which gives what, 9? So the answer is 9, 729. All right, so I think if you look at the two worksheets, that should be enough to help you with worksheet number 7 and worksheet number 8. Worksheet number 7. Now, let me remind you one other thing, and that's this. And this is kind of review from last week's worksheets that were due to yesterday. If you have y equals, let's say, 3 to the x minus 20. Again, what's a horizontal asymptote? Nope. -20 is not the horizontal asymptote. What is a horizontal asymptote? Huh? You got to speak louder. Say it again. No, I needed you to say y equals. Y equals, y equals, y equals. You'd be surprised on those worksheets that y'all turned in, when I asked for the horizontal asymptote, you'll put a number. And on those videos, I said, do not put a number. Horizontal asymptote is a line. You got to name it using an equation. So you have to say y equals -20. All right? So you have to utilize all those resources that are there for you So the horizontal asymptote is y equals negative 20. If you just put 20, you're going to be very upset because I can't give you full credit because mathematically that's not correct. All right, now the other question you're going to have to answer on test number 4 and on your final exam is this. What is the domain of an exponential function? So it's all real numbers, because in fact, if you look at the one we drew earlier, when you look at the domain, when you go from left to right, you're going from negative infinity all the way to positive infinity, regardless of which one you're looking at. But the range is not all real numbers. You can see here, if you look at the red graph, the range goes from the horizontal asymptote all the way to what? Infinity. Now remember, the horizontal asymptote here is y equals 0. Remember that? The graph never touches the horizontal asymptote on an exponential. It never crosses it. So when you find the range, I'm going to put the range for this one. When you look at the range here, the range is going to be from 0 to what? Infinity. Can I include 0? Does the graph ever touch 0, y equals 0? No. So you're going to put parentheses 0 to infinity. So when discussing the range for an exponential, you're never going to use a bracket. Whereas on test 3, test 2, test 1, when you're asked to find the domain and range of some of those functions you have to look at, brackets were necessary. Here, you don't use a bracket. So you have to get used to the type of function you're dealing with. So an exponential, the range is parentheses 0 to infinity for this graph. Now when I go back down here to the one we're looking at, y equals 3 to the x minus 20, we know the domain for all exponentials is all real numbers. But the range is not. So without graphing, how can you determine the range? Without actually doing all that graphing. In your mind, how can you determine the range of this function?
Find the horizontal asymptote.
Find the horizontal asymptote, which is what?
Y equals
Negative 20. The next thing you're going to ask yourself is this. Is the graph above or below the horizontal?
maybe above.
It'll be above. When would it be below? That's that reflection. When will it be below?
Yeah, the first one's negative.
If you have a negative out here, that's a reflection about which axis? X-axis. So that would be below the x-axis. That would be below the horizontal asymptote. So y equals 3 to the x minus 20, that's going to be above the horizontal asymptote. So in your mind, you have something that looks like this. Here's negative 20, and it'll look something like this. Notice I didn't find any points. I just knew that it was above the horizontal asymptote. So what's the range? Negative 20 to infinity. Parentheses or brackets on negative 20? Parentheses, because the graph never touches the horizontal asymptote. What if you had this? Y equal negative 1/2 to the x plus 30. Y equals negative 1/2 to the x plus 30. What's the horizontal asymptote?
Y equals 30.
Y equals 30. The domain is always going to be all real numbers for an exponential. When you talk about logarithms, that's Friday's material, not Friday's, Thursday's material. When you talk about logarithms, that's not the same anymore. But for an exponential, the domain is all real numbers. The range, how would you find the range on this one? Without knowing any points, how would you find the range?
With the horizontal asymptote.
You look at the horizontal asymptote, which is y equals 30. So here's a horizontal asymptote, y equals 30. What else do you need to ask yourself? Is the graph above or below the horizontal? What is it? Below. Why is it below? Okay, this is the reflection. Okay, reflection. So it'll be below. All right, it'll do something like this. I don't know if it crosses it here, the x-axis. It may cross it here, I don't know, but at least it's below, right? So how would you find the range in this case? This one's a little bit more difficult. How would you find the range? You would say what? Negative, you can always go from bottom up for the range. Negative infinity all the way to 30 with parentheses. All right. Okay, so that should be enough for worksheet 7 and 8 for 5.1. Okay, so now the next part talks about, this is Tuesday's material, which you looked at yesterday. So yesterday you looked at section 4.4. All right, section 4.4. All right, so this 4.4 talks about zeros of a polynomial function. Zeros of a polynomial function. So when you talk about a zero of a polynomial function, you've dealt with that since last semester. When you solve these quadratic equations, you are finding zeros. So a zero of a polynomial function is where the function is 0. So where y is equal to 0. And in the plane, in a coordinate plane, where is y equal to 0? In a coordinate plane, where is the y? Where are the y values equal to 0? On the x-axis. So your x-intercepts are also considered zeros. X-intercepts. So when you talk about zero polynomial function, you're looking at where the function is 0, which also are the x-intercepts. So whenever you graph functions and you have to find the x-intercepts, what you were finding were zeros. Where is a function equal to 0? That's what you were finding. So let's look at these examples. We're going to start with some simple examples. So let's find the zeros. Number 1, g of x is equal to x minus 5 divided by 2x plus 3. So I have this function, and I want to find the zeros. You have enough information from last week and even from the end of last semester to be able to answer that question. How would you find the zeros for this function? Good. It's already in factored form in it. So this is what kind of function, if you were to multiply this out, what kind of function is this? Quadratic. That's a quadratic function. This is 2x squared, the outer is 3x, so what's that, minus 7x? Minus 15? You have this quadratic function. In last semester and also the beginning of this semester, you had to solve a quadratic function. And when you solve a quadratic function, when using the quadratic formula, you are setting the function equal to 0. But it's already in factored form. So all you do is set each of those factors equal to 0. So we have x minus 5 equals 0. So we have x equal 5. 2x plus 3 equals 0. So you get x to be negative 3 halves. So those are your zeros. So those are your zeros, 5 and negative 3 halves. There's a couple of more terminology, though, that you have to learn in this lesson, in this section, in section 4.4. They also talk about zeros with a multiplicity. Zeros with a multiplicity. Okay, multiplicity. So when we talk about multiplicity, basically you're asking yourself, how many times did that zero occur as a zero? How many times does this zero, or let me write it as this number, how many times does this number occur as a zero? So if you look at x equal 5, how many x equal 5s do you see here? 1. How many x equal negative 3 halves do you see? 1. So we say the zeros are 5, and they ask you about multiplicity. You're going to say multiplicity 1 for each of them. So zeros are 5 with multiplicity 1. And then negative 3 halves with multiplicity 1. Make sure you make the connection between multiplicity and the factor. So remember when I solved for x equal 5, that came from which factor? X equal 5 came from which factor? X minus 5. How many factors of x minus 5 do you see? 1. X equal negative 3 halves came from which factor? 2x plus 3. How many factors of 2x plus 3 do you see? 1. Okay. Number 2. H of x equals x minus 3 cubed times x plus 4. The good thing about this one is that it's already in factored form. So how do you find the zeros? Set each factor to 0. So if you look at that first factor, x minus 3, when I set that equals 0, what's my 0? X equals 3. So 3 is your 0. When I look at my other factor, x plus 4, and I set that equals 0, what's my 0? Negative 4. So this function has two distinct zeros, 3 and negative 4. But they have different multiplicities though. So we can also say this. We can also say x equal 3 is a 0 with multiplicity. And what's a multiplicity? 3, just your exponent. X minus 3, see, x minus 3 cubed really means x minus 3 times x minus 3 times x minus 3, right? And we set each of those equal to 0, you get x equal 3 how many times? 3, but you only listed once. So your 0 is 3 with what multiplicity? 3. X equal negative 4 is a 0 with what multiplicity? 1. Okay? All right. Number 3. Suppose you had h of x equal x plus 2. Let me make it 3. I don't want to use the same exponent as the number. X plus 3 squared times x minus 5. So finding the multiplicities here are easy because they're in factor form, but they're not going to be in factor form. Just keep that in mind. But understanding the idea of multiplicities, you need to understand this factor form and the exponent. So how many zeros does this function have? 2. You have 2 factors, x plus 3 occurring twice, and then x minus 5 occurring once. So to find the zeros, you're going to take each of those factors and set them equal to 0. So one of them is negative 3, right? The other one is 5. Okay, let's talk about multiplicity. So x equal negative 3 is a 0 with what multiplicity? 2, because x plus 3 occurred twice as factors. X equal 5 is a 0 with what multiplicity? 1. Okay, now one of the topics, and I think this was probably last week or it could be this week, one of the topics that you either learned or will learn is this. When a 0 has an even multiplicity, when a 0 has an even multiplicity, the graph touches the x-axis at that point, at that 0. So remember earlier we said the zeros are your x-intercepts? So hence I'm using the word x-axis. So when a 0 has even multiplicity, the graph touches the x-axis at that 0. When a 0 has odd multiplicity, the graph crosses the x-axis at that 0. And it's easy to understand because look, if you think about a quadratic function, so the one we had earlier was this. Let me go find the one we had earlier. This one here, where we had 2x squared minus 7x minus 15. So if I have this, f of x equal 2x squared minus 7x minus 15, I think that was the one. Yes, that's the one. So this is a quadratic function, right? We found the zeros, which are the same thing as the x-intercepts. If we go back, we found the zeros to be, or the x-intercepts to be what? 5 and negative 3 halves, okay? And the multiplicities were what for each one? 1. They were odd though, right? So your x-intercepts, which is the same thing as your zeros, 5 and negative 3 halves, right? So if you do a rough sketch of this, now go back and look at your function right here that we're looking at. Does the parabola open up or down? Opens up because the coefficient of x squared is positive, right? So it opens up. So my x-intercepts are here at 5 and at -3/2, which is -1.5. So let's say that's here. So the graph looks something like this. Notice those x-intercepts. Does the graph touch or crosses the x-axis? It crosses the x-axis, crosses the x-axis. It correlates to the multiplicity. The multiplicity for each one of those was what kind of number? An odd number. Now, if you look at this one, let's say we had this quadratic function. How would you find the zeros? You could factor. If it doesn't factor, you would have to use the quadratic formula. But let's go ahead and factor this. When you factor this, you get x minus 5 times x minus 5, right? So what's the zero? X equal 5, but what multiplicity? 2. So that means that if I were to graph this, would it cross the x-axis or touch the x-axis at 5? It would touch. In fact, here's the graph. This is the graph right there. There's the graph. In fact, it makes sense because look, if I write this as x minus 5 squared, right? And I wanted to use translations. In terms of translations, this says I've graphed the parent function. What's the parent function? X squared. And I shifted which way? And so which translation is it? Horizontal or vertical? Horizontal. Which way do I shift it? To the right. And that's what you see here. So whenever the multiplicity is even, it touches the x-axis at that 0. If it's odd, it crosses. So when you work on noon assignment for this section, there's one topic in that section in noon algebra that talks about the multiplicities and the graphs. So if I go back to the one we saw earlier, this one, and I think it was, let me just go ahead and use this one. So for this one, where I have x minus 3 squared times x plus 4, the zeros are 3 with what multiplicity? Multiplicity 2. What's the other one? 4 with what multiplicity? All right, here's what the graph would look like. Now, in terms of knowing where the turning points are, I think in the last week, you'll learn about turning points. That was one of the worksheets I had to turn in. So the graph looks something like this. Now you get better at graphing this when you use derivatives. So next, if you take calculus, you'll be able to do a better job with finding out where that turning point actually occurs. You would use derivatives for that. But the graph, so at 3, here's 3, and then here's -4 right here. All right, here's the other thing I want to see if you remember. Last week, you learned about end behavior. Tell me something about the end behavior of this function. Let's see if you remember that. It's on test number 4. End behavior. How would you determine the end behavior of this function? You need to know the leading term. How would you find the leading term of this function? It's already factored. How would you find the leading term? All right, guys. All right, this is on test number 4 and also your final exam. Y'all turn in a worksheet on this. We're going to start with a simple one. To find the leading term, one thing you could do is multiply this whole thing out, but you don't want to do that. That could take you 5 to 10 minutes to do that. You've learned another way to do this, to find the leading term last week. So if it's already in factored form, all you have to do to find the leading term without having to multiply all this out is to find the leading term of each factor. What's the leading term of this factor right here? Leading term is a term with the highest exponent. What's the leading term of that first factor? X. What's the leading term of that second factor? X. What's the leading term of that third factor? X. If you multiply all this out, what's x times x times x? X cubed. So if you were to multiply all those 3 factors out, which would take you about 5 minutes, you would find out that the leading term is x cubed. So the leading term is x cubed. Once you know the leading term, you know about the end behavior. So the exponent is odd. Exponent is odd. And the coefficient is positive. So tell me something about the end behavior of this function. What happens on the right? What happens on the left? Whenever there were 4 functions in the lesson, when y'all did that worksheet, I asked you to look at 4 functions that would help you with all of these problems. And that is x cubed. X cubed looks like this. On the right, as x goes to infinity, what does your y value do? What's happened to those y values? Y values are going to what? Infinity. So it rises on the right, and it does what on the left? Say the word falls. Falls. Rises, falls. Falls on the left. So as x goes to negative infinity, what does your y value go to? It's going down. What does your y value go to? Negative infinity. So whenever the exponent is odd and the coefficient is positive, you think of x cubed. What does x cubed look like? It rises on the right, falls on the left. That same pattern is going to approach this as well, even though it's a different function. All you can tell me is this. On the right side it rises, on the left side it falls, and it does some other stuff here. It's a continuous function. What would be the leading term of this function? If you were to multiply all this out, which you would not, it would take you much longer than the previous one. But how would you, if on your test and your final exam, they ask you, how do you find the leading term, or I'm sorry, what's the end behavior? To find the end behavior, you have to find your leading term. How would you find the leading term? You find the leading term of each factor. What's the leading term of the first factor? 2x. What's the leading term of the second factor? But it's being raised to the second power, so it's x to the second power. What's the leading term of the third factor? So if I multiply that out, 2x times x squared times x equals what? 2x to the fourth. So this time, my exponent is even. So since the exponent is even, think of x squared. When you think of x squared, the in behaviors are all pointing in the same direction. Either they're pointing up or they're pointing which way? Down. Every even function has that in behavior. I shouldn't have used the word even function. Every function that has a leading term with an even exponent has that behavior. A function that has a leading term with an odd exponent, the arrows are pointing in different directions. So in this case right here, where I have g of x, and I found this to be my leading term, once you find your leading term, you know your end behavior. So my exponent is even and my coefficient is positive, so I know that they're both going to be pointing in the same direction. They're going to be pointing which way? Up. So on the right it rises, on the left it rises, and it does some other stuff here. All right. Now, let's go back to this one here. So I know that my zeros here are 3 with multiplicity 2. So it touches or crosses? Touches. So it's going to touch here, right? Touch. At -4, does my graph touch or cross? Cross, because the multiplicity is odd. What I asked you, though, was this. To determine what the end behavior is, you need to know the leading term. You should now be able to tell me what the leading term is for this function. What's the leading term?
The x to the third.
X to the third. So if you look at the leading term of each factor, this one's x, and that's being squared, and this one here is x, and x times x is x cubed. So the leading term is x cubed. If you were to multiply all this out, you would get x cubed. So my leading term has an odd exponent, and the coefficient is positive. So think of x cubed. X cubed, remember, rises to the right, falls to the left. So that means that on this side, it'll do something like this, and on this side, it'll do something like this. Okay? And in fact, you don't have to graph this. They're not going to ask you to graph this, by the way. You're going to graph this in calculus, but it'll look something like this. Let's see, it crosses it here, so it'll do something probably like this. Like this. And then it will go up and then come back down and then touches it here. So that's what the graph would look like. Now that turning point, it could be somewhere up here. You would need derivatives to actually find out where that turning point is. Okay? So knowing the behavior can help you to actually draw these a little bit better. But there was a worksheet last week that talked about end behavior. It's on test number 4. So notice all of you struggled with my questions. So when you look at that study guide and you look at those worksheets, make sure you look at the key that's posted with it. Okay, let's continue on with this. Okay, one of the worksheets that goes with this is worksheet number, there are two of them that goes with what we're looking at now. Worksheet 4.4, worksheet 1 and 2. So 1 and 2. So 1 and 2 deals with all of this right here. So let's look at this example. Suppose I ask you, or I tell you that f of x is 3x squared plus 10x minus 8. And I want you to find the 0. What would you do? Yeah, it's quadratic function. Y'all dealt with quadratic functions last semester, the end of last semester, and the beginning of this semester. So to find the zeros, you set the function equals 0, right? So you're saying 3x squared plus 10x minus 8 equals 0. Either you use a quadratic formula or you factor it. This one's factorable. So when you factor it, let's see, you're going to get 3x minus 2, and then x plus 4. 3x minus 2 and x plus 4. And then what do you do to each of those factors? Yeah, so what are your zeros? There are two of them. What are they?
Is it x equals 2/3?
2/3 is the first one. What's the other one?
X equals
Negative 4. So that's how you find your zeros. So that worksheet number, if you look at it, that worksheet number 1 for section 1. For section 4.4, it says find the zeros of each quadratic function. So 1 through 5 are factorable. But let me just show you. Now this is not graded, but you need it for another lesson. So let me show you about number 6. So suppose you had this example. F of x equal x squared plus 9. So this is not factorable, by the way. This example, f of x equal x squared plus 9. It's not factorable. But you can still find where this function is equal to 0. And you had this this semester. How would you solve for x? What's the best way to solve for x here? Rather than using quadratic formula, what's the best way to solve for x? Square root property, because the x term is missing. So you're going to get x squared equal negative 9. And then would you do the both sides? You had this on a test. In fact, one of the problems said use the square root property. So you're going to take the square root of both sides. Which you get the worksheets that are due this week, or the 24th. So when you take the square root of both sides, remember that plus or minus? So you get x equal plus or minus the square root of a negative 9. But what is the square root of a negative 9 the same as? 3i. So this becomes x equal plus or minus 3i. So those are your zeros. They're not real numbers, they're imaginary numbers, but they're still zeros. Okay? All right, so that's how you would do something like number 6. All right, now let's continue on with this. So that was that worksheet number 1 on section 4.4. All right, let's look at worksheet number 2. Okay, this is worksheet number 2. All right, worksheet number 2. Okay. So we're going to continue talking about characteristics of zeros. multiplicities, and factors. So characteristics of zeros, multiplicities, and factors. So earlier, I'm going to pull this down, and earlier right here, see this right here where we said x minus 4 was a 0? X equal negative 4 is a 0. So if negative 4 is a 0, then what is a factor of that polynomial? So if you know the 0, you know a factor. If negative 4 is a 0, what is a factor of that polynomial? It's x plus 4. That's how you got it, right? So if x equal negative 4 is a 0, then x plus 4 is a factor, because that's how you got that 0. You said x plus 4 equal to 0, right? So then if I ask you if x equal 3 is a 0, then what is a factor of a function with a 0? So if x equals 3 is a 0, then what will be a factor of a function with that 0? X minus 3. All you're doing is bringing the constant to the other side. So if x equals 3 is a 0, then x minus 3 is a factor. Okay, let's look at some examples. Number 1, if x equal negative 5 is a 0 of f of x, then what must be a factor of f of x? So you can tell me one factor now. What is it? X plus 5. Because that's how you get x equal negative 5. You bring the negative 5 over, you get x plus 5, right? And so to get the 0, you're basically taking x plus 5 and setting it equal to 0. Okay, now let's look at this one. If x equal 2/3 is a 0 of f of x, then what must be a factor of f of x? And you don't want any fractions in your answer. Don't want any fractions, no fractions. So don't say x minus 2/3. No.
3x minus 2.
Okay, good. The answer is 3x minus 2. All right, so here's what he did. So basically he did what I told you not to do. So in his mind, he knows that I can write this as x minus 2/3 equals 0, right? And then you clear your fractions. You multiply both sides by the LCD. What's the LCD? 3. So you multiply both sides by 3, which you do to the right, you do to the left, and then you distribute. 3 times x is 3x. 3 times a negative 2/3, the 3's divide out, you're left with a negative 2 equal, and then 0 times 3 is 0. And so there's your factor. Just make sure that on that worksheet there are some fractions, so make sure you don't write the answer as x minus 2/3. I will not accept that. You need to clear those fractions. Okay? All right, number 3. Write a polynomial function for g of x in which the 0 is x equal -5 with multiplicity of 4. You do. So write a polynomial function for g of x in which a 0 is x equal -5 with multiplicity 4. Well, if x equal -5 is a 0, what's a factor?
X equals -5, x plus 5,
X plus 5. So, and what's the multiplicity?
4.
4. So that means x plus 5 occurs as a factor how many times?
4 times.
4 times. So you're going to say x plus 5 raised to what power? 4. And there's the answer. You wrote a polynomial function. It's in factor form. Now, I also want to say this. There are an infinite number of answers, though. There's an infinite number of answers. Could this be an answer as well? Does that still satisfy the conditions? 2 times x plus 5 to the 4th power? What's a 0 in both of these cases? -5. What's the multiplicity? 4. You could also say this. -1/3 times x plus 5 to the 4th. Meaning that your coefficient could be any real number, right? Most students, though, will leave it as this. They'll leave the coefficient as 1 right here. But all those have multiplicity 4 for 0, -5. Number 4. Write a polynomial function h of x in which x equal -4 is a 0 with multiplicity 2. X equal 5, 6 is a 0 with multiplicity 3. X equal 2 is a 0 with multiplicity 1. So you have 3 distinct zeros with different multiplicities. And you want to write a polynomial function. So you'd say h of x equal, and then what would you say? If x equal -4 is a 0, what's a factor?
X plus 4,
With what multiplicity?
2.
2. If x equal 5, 6 is a 0, what's a factor without fractions?
6x minus 5.
6x minus 5. With what 0? I'm sorry, what multiplicity? And then if x equal 2 is a 0, what's a factor?
X minus 2.
With what multiplicity? 1. So there's your answer. Now notice my coefficient of 1, but y'all can put any other coefficient if you want to. It still satisfy these conditions. Okay? All right, so that should help you with worksheet number 2. Okay, so that's how you would do those. All right, then the next thing I want you to look at is look at worksheets 3 and 4. 3 and 4. Okay, so one of the things that you learned last week was long division. And you're going to have long division on your test number 4, and they may, sometimes they do, not always, will have long division in your final. But let's see if you remember how to do this. Let's go ahead and divide x cubed minus 3x plus 12x squared plus 4 by x minus 2. By using long division. All right, so if you were to use long division, how would you do this? What? Okay, you got to put them in descending order first. So this is x cubed plus 12x squared minus 3x plus 4. And so in doing long division, remember you have a divisor and a dividend. So your divisor goes here, and that's going to be x minus 2. And your dividend goes here, and that's going to be x cubed minus 3x, oops, descending order, plus 12x squared minus 3x plus 4. And remember, if there are any missing terms, what do you have to put in its place? 0. All right, and so you do the long division. So you take the first term and divide into the first term. So x into x cubed is equal to what? X squared. So put that here, x squared. Then you multiply x squared times x minus 2. X squared times x. Now if you do this correctly, those two terms have to be exactly the same. X squared times a negative 2. All right, and then what do I do at this point? Subtract. You subtract both those terms. So x cubed minus x cubed is 0. Remember, that always has to happen. 12x squared minus a negative 2x squared means 12 plus 2, which is what? 14x squared. Then you bring down the next term. Then you do the division all over again. X into 14x squared is equal to what? 14x. Notice I'm aligning my like terms. Then you do multiplication over again. 14x times x is 14x squared. If you're doing this correctly, these terms have to be identical. And then 14x times a negative 2 is a negative 28x. Is that right? And then what do you do at this point? You subtract. And if you do this correctly, 14x squared minus 14x squared, that better cancel out. Now what's a negative 3x subtract a negative 28x? That's negative 3 plus 28, right? 25. And then plus 4. Then you do the division all over again. What's x into 25x? Then you multiply 25 times x, 25 times a negative 2, and then you subtract. If you're doing this correctly, these have to cancel out. 25x minus 25x is 0. What's 4 subtract a negative 50? That's 4 plus 50, which is 54. And so that was your remainder. Now in that worksheet, you were asked to write it like this. You were asked to say x cubed plus 12x squared minus 3x plus 4 divided by x minus 2 is equal to the quotient. What's the quotient? This is your quotient. Remember, that's your quotient. So it'll be x squared plus 14x plus 25 plus a remainder, which is 54, divided by the divisor, which is x minus 2. All right, so that was a review from last time. Okay, now, if, again, use that same function, let's suppose we had, my function was the same one we had right here, x cubed minus 3x plus 12x squared plus 4. All right, and suppose I asked you to find f of 2. So if you want to find f of 2, what would you do? You have a calculator, what would you do? You'd plug in 2 into your function, right? So every other variable x, you would substitute 2. So I'd have 2 cubed plus 12 times 2 squared minus 3 times 2 plus 4. And I know that 2 cubed is 8, 2 squared is 4, 4 times 12 is 48, minus 6 plus 4. 8 plus 48 is 56. 56 minus 6 is 50. And 50 plus 4 equals what? 54. That's the same thing as the remainder in it. And you may say, well, if you look at your divisor right here, x minus 2, and if I set that equal to 0, I get x equal what? 2. So if you were asked to find f of 2, and they tell you not to substitute, like we just did, then what they're asking you to do is this. Find the remainder, when the function is divided by x minus 2. And so you could use long division, or in this case, x minus 2 is linear, you could use synthetic division. Remember synthetic division? Last time? Okay, watch synthetic division. Let me remind you about synthetic division. So let's do this. So divide 3x to the 4th minus 4x cubed plus 7x minus 5 by x plus 3 using synthetic division. Rather than long division. So why is it in this case I can use synthetic division and not necessarily long division? What allows me to use synthetic division here? No, not because of that. It's a linear factor. This is linear, right? Linear factor. And the coefficient of x is 1. So whenever you have a linear factor and the coefficient of x is 1, you can use synthetic division. And to use synthetic division, first of all, you're going to set that equal to 0. And solve for x. So x, when I divide this polynomial by x plus 3, the remainder I get the remainder you get here will be obtained by using those coefficients. So what are the coefficients here? 3, your coefficient of your quotient, I'm sorry, your dividend. 3, what's the next one? What's the next one?
7.
Nope. There's a missing term.
0.
X squared is missing, so you have to put what? 0. What's the next one?
7.
And what's the next one?
-5.
-5. Okay, so when using synthetic division, you remember what was the next thing you had to do? Bring down the 3. Then what'd you do? Multiply. -3 times 3 is? Then what'd you do? You added. -4, -9 is? -13. Then what'd you do? Multiply. -3 times -13. Then what'd you do? 0 plus 39 is? Then what'd you do? -3 times 39, I think it's -117. And then you add 7 and a -117 is a -110. Then you multiply. -3 times -110 is a positive 330. And then you add, you get 325, is that correct? So the remainder is 325. So one of the things that tells you is this. So if I asked you, then what is f of -3? Then you're going to say what? 325. And if you actually took -3 and you substitute for x, you would see you do get 325. So that's the idea of that remainder theorem. There's something called the remainder theorem. Remainder theorem. And it says this. If a polynomial I'll show you this. All right, a polynomial function, it's just not writing. F of x, Jesus. This room is so awesome. God dang it. All right, if a polynomial function f of x is divided by x minus a, the remainder is Jesus. P of A. I'm trying to get, all right, it's there's something wrong with this board now. So it's P of A. So in other words, this remainder that you would get is the same thing as if you would just say F of A in this case. All right, it's almost 7:45. There's that worksheet. For 3 and 4, we couldn't get to that. So let me remind you where to go for the lessons. So All right, so we're on the rational zeros theorem, so that's Tuesday's material. So here are the lessons right here. So study the lessons for topic 24, part B. That goes with these two worksheets. So you click on it. It's important that you look at all four. It's a very detailed lesson section. So you have to know something about rational zeros theorem. Then there's some examples about cubic functions. We talked about quadratic already. And then these are the steps for finding the rational zeros of a polynomial function. And continue talking about cubic functions. So the one on the worksheet is just cubic. So if you look at worksheet number 4, worksheet number 4, notice they're all cubic. X cubed, 2x cubed, 4x cubed. The one in your final, and they do have one in your final, that has to use the rational zeros theorem, is cubic. So that there's enough lessons there to get you through this. There's no way I could have finished this within 5 minutes. All right. And those worksheets are not due until the 24th. Is that correct? 24th. So they're not due this Sunday. They're due the 24th. And when's your test number 4? Yeah, the Wednesday you come back. And I showed you where the study guide was. It's listed 3 places, so you can't say you didn't see it. All right. I'm going to quickly call the roll. And there's always something wrong with this room. I don't think we've ever had a class where this thing worked well. I'm going to go ahead and do the online first. Lindley is here. Nadia. Destiny. Rebecca. Demetra. Anyone else? Dyer? Okay, so is that all the online? All right, thank y'all. Have a good Easter. All right, rest of you. Your last name?
Cardenas.
Okay. It's easier just to say last names in alphabetical order. Last name? Yeah. Okay. Last name? Last name? Last name?
Johnson.
Just say last name, it's easy. Next, last name. I'm sorry? Okay. Next. Last name? All right, have a good Easter. And those worksheets that due tonight are actually due tomorrow if you didn't finish them. They're due tomorrow. Okay.
But it's a little long.
Yeah. All right. Thank you.